Welcome to the Menga podcast, your ultimate dose of vulnerability. Today, we're diving deep into a part of Windows that you might not be familiar with. It's called the Common Log File System,
Right.
or CLFS for short.
Yeah, CLFS.
It's one of those behind-the-scenes components that most people never think about,
Yeah,
but it plays a really critical role in keeping your system stable and secure.
absolutely. You can think of CLFS like a meticulous record keeper for your computer.
Okay, a record keeper.
Yeah, so imagine you're making like a big purchase online, and you want to be absolutely sure that that transaction goes through smoothly, that your payment and your order details are recorded accurately.
Right.
CLFS helps with that, and not just for online shopping,
Okay.
but for all sorts of critical system operations.
So it's about guaranteeing things happen the way they're supposed to, even if there's a hiccup along the way.
Exactly. It's all about ensuring data integrity and consistency, especially when it comes to these system transactions. And to understand the vulnerability we're diving into today, we need to peek under the hood a little bit and see how CLFS actually works. And we've got some really interesting source material to guide us, detailed technical documentation from a security researcher who really knows their stuff.
Okay, so let's unpack this. The researcher's documentation is focused on the internal structure of CLFS, right?
Yes.
What are some of the key things you picked up from that?
Well, the first thing to understand is that CLFS is structured around this thing called the base log file, or BLF.
BLF, got it.
It's basically the core data store where all the logging information is kept. And to ensure that the data in this BLF stays protected and intact, CLFS uses a really clever system of log blocks and sectors.
So imagine the BLF as like a big filing cabinet. Each log block is like a separate file folder holding important information.
Yeah, that's a great analogy. And these sectors you mentioned are like the individual pages within each file folder.
Okay.
Now, here's the key part. These sectors are written to the BLF in a way that prevents them from being partially written.
Oh, interesting.
It's an all-or-nothing kind of deal.
Why is that so important?
Well, because if a sector were to be only partially written, say due to a sudden power outage or system crash, you could end up with corrupted data.
Right.
That's where these atomic rights come in.
Okay.
They guarantee that either the entire sector is written perfectly or nothing is written at all.
Okay, so that's one layer of protection. But what about ensuring that the data itself hasn't been tampered with? Is there a way to verify that?
Absolutely. Each of these log blocks starts with a header.
Okay.
And this header includes something called a checksum.
Checksum.
Think of it like a digital fingerprint that confirms the data's authenticity. If the data is modified in any way, the checksum will no longer match, and that'll alert the system that something's wrong.
So it's like a tamper-proof seal on each file folder, ensuring that nobody snuck in and changed anything.
Precisely.
Okay.
But here's where things get interesting.
And this is where the vulnerability comes in. The researcher discovered that there's a flaw in the way the CLFS driver handles this checksum verification process.
Wait, so there's a chance that someone could tamper with the data and the system wouldn't even notice.
That's the scary part. Specifically, the vulnerability lies in the handling of a function called CLF's decode block.
CLFS decode block.
This function is supposed to decode a log block and verify its checksum. But in certain situations, the CLFS driver doesn't properly check the return value of this function.
So it's like the security guard clocking out without actually checking everyone's ID.
Exactly. And that opens up a window for an attacker to slip through. They could potentially manipulate the checksum, corrupt the data within the log block, and the system would be none the wiser.
Okay, that sounds bad. But how would an attacker actually go about doing this? It's not like they can just open up the BLF in a text editor and start changing things, right? No, it's much more complex than that. But the researcher who discovered this vulnerability, they actually figured out a way to exploit this weakness. And it's quite ingenious, really.
All right, let's hear it. What's the attack plan?
Well, the first step is to understand that the attacker can't just randomly corrupt data within the BLF. They need to target very specific data structures to achieve their goal. Remember those different node types mentioned in the documentation?
Yeah, like different categories of information.
Yeah, each data structure within the BLF is assigned a specific node type code.
Okay, so each file folder in our analogy has a label that tells the system what kind of information is inside.
You got it. the attacker needs to manipulate the data structures in a way that exploits the checksum verification flaw.
Right.
And causes these node types to be misinterpreted.
So they're not just vandalizing random files, they're carefully rearranging things to create chaos.
Exactly. And the researcher's documentation outlines a step-by-step method for doing this.
Yeah.
It involves some pretty advanced techniques like strategically moving and overlapping data structures within the BLF. Oh, wow.
Well, forging a specific checksum value and ultimately gaining control over how those node types are interpreted by the system.
That sounds incredibly complex. Is this something that the average person could pull off?
It definitely requires a high level of technical skill and knowledge of how CLFS works.
Yeah.
But the point is, this vulnerability exists.
That's right.
And it has the potential to be exploited.
Okay.
The researcher who discovered this actually won first place in a hacking competition by demonstrating how they could use it to gain control of a Windows 11 system.
Wow. So they were able to turn this seemingly minor code oversight into a full-blown security breach.
That's right. And it all started with the CLFS driver failing to properly check that return value from the CLFSBaseFilePersisted function.
Okay, we've got a vulnerable system, a clever attacker, and a plan in place.
Yep.
What happens next? How do they actually use this corrupted data to take control of the system?
Right.
That's where we'll pick up in part 2 of our deep dive.
Sounds good. All right, so we left off with our attacker successfully corrupting the BLF.
Right.
And causing the system to misinterpret those critical node types.
Yeah.
So now they need to leverage that confusion to gain control.
Okay. They've created the chaos. Now it's time to capitalize on it.
Exactly.
So what's the next step?
Their target is something called the client context.
Client context.
This is a data structure within the BLF that stores information about the user or application that is interacting with CLFS.
So it's like an ID card that tells the system who's allowed to do what.
Exactly.
Mm-hmm.
And the researcher figured out how to exploit the corrupted BLF to essentially forge a fake client context.
Oh, wow.
Remember how we talked about those data structures overlapping because of messed up node types?
Yeah.
Well, by carefully manipulating those overlaps, they can trick the system into reading data from the wrong place when it tries to access the client context.
So it's like they've created a phantom ID card and the system is fooled into thinking it's legitimate.
That's a great way to put it. And the documentation gets really specific.
It outlines exactly how they manipulate the offsets and sizes of those overlapping structures.
Right.
It's pretty technical, but the key takeaway is that they're able to control what the system sees when it looks at the client context.
Okay, so they're in disguise.
Right.
But what's the end game here? What do they do with this fake client context?
This is where it gets really interesting. Within that client context, there's a crucial piece of information, a pointer to something called the CLFS container class.
CLFS container?
This class is part of the CLFS driver itself, and it handles a lot of the core functionality.
Okay, a pointer, remind me again what that is in this context.
Think of it like a street address that tells the system where to find a specific piece of code. In this case, the code for that CLFS container class.
Okay.
Normally, this pointer points to a location within the protected kernel memory space.
Okay.
That's where the actual CLFS driver code resides.
So it's a way to access the inner workings of CLFS.
Right.
But it's supposed to be tightly controlled.
Exactly. But because the attacker has control over the client context, they can manipulate this pointer.
Okay.
Instead of pointing to the legitimate CLFS container class within the kernel, they can redirect it to a fake version that they've cleverly constructed in user space memory.
Wait, user space, isn't that like the less secure part of the system where regular applications run?
You got it. And this is a brilliant move because user space is much easier to manipulate than the protected kernel space.
Ah, so they've essentially created a backdoor into CLFS by redirecting that pointer.
Precisely. Now, anytime the system tries to interact with the CLFS container class through that pointer, it's actually interacting with the attacker's fake version in user space.
Okay, this is starting to sound like a heist movie with all these layers of deception. What do they do with this newfound access? Do they just start messing things up within CLFS?
That's certainly one possibility.
Okay.
But the attacker in this case has even bigger plans. Their goal is to escape the confines of user space and gain full control over the operating system.
Whoa, that escalated quickly. But how do they jump from manipulating CLFS to taking over the entire system? That sounds like a huge leap.
It is a big leap, but the documentation outlines how they pull it off.
Okay.
It all hinges on a clever manipulation of something called the previous mode value in the kernel.
Previous mode. What's that all about?
It's a mechanism that the operating system uses to track whether code is running in user mode or kernel mode. Think of kernel mode as the system's control center where all the sensitive operations happen. User mode is where regular applications run with limited privileges.
Got it. So they're trying to break into the control center by messing with this previous mode value.
You got it. By manipulating certain values within their fake CClfs container class, they can trick the system into thinking that their user space code is actually running in kernel mode.
Whoa. So they're forging their security clearance to gain access to the most sensitive parts of the operating system.
Precisely. And once they've achieved that, they can essentially do whatever they want.
Okay, they've infiltrated the control center. This is the part where we find out if they're a mastermind or just a vandal. What's their next move?
Well, in the case of the researcher who documented this vulnerability, they wanted to demonstrate the impact of the exploit without causing any real damage. So instead of wreaking havoc, they chose to prove their control by spawning a new process.
A new process, like opening a program. What did they choose to run?
They launched a simple command prompt, cmd.exe. But here's the kicker. They ran it under the context of winlogon.exe.
WinLogin, that rings a bell. Isn't that related to the login screen?
Exactly. WinLogin.exe is a critical system process that runs with the highest level of privileges, what we call system privileges.
So by spawning a command prompt under the context of WinLogin.exe, they're essentially creating a backdoor with admin access.
You got it. They've effectively demonstrated that they can execute code with the same level of access as the operating system itself.
That's a powerful demonstration of just how dangerous this vulnerability could be in the wrong hands.
Absolutely.
But we've covered a lot of ground here, and I think it's time to take a breather and process all this information.
Yeah, good idea.
We'll pick up the story in part 3 of our deep dive and explore what happens next. So to recap this on, researcher was able to exploit a tiny oversight in the CLFS driver. And gain complete control over the system. That's pretty mind-blowing.
It really is. It really highlights how even seemingly minor vulnerabilities can have huge consequences when exploited by someone with the right skills and knowledge.
Yeah, for sure. But let's talk about what happened after they achieved system-level access. Did they just stop there? Or did they take things further?
Well, in this case, the researcher was actually very responsible. And they reported the vulnerability to Microsoft instead of using it for malicious purposes.
That's good to hear.
Yeah, their goal was to demonstrate the vulnerability's potential impact, not to cause any harm.
It's always reassuring to know that there are people out there working to make our systems more secure. But let's imagine for a second that this vulnerability had fallen into the wrong hands. What kind of damage could a malicious attacker have done?
Oh, the possibilities are pretty terrifying, honestly. With system privileges, an attacker could do just about anything. Steal sensitive data, install malware, even take complete control of the computer and use it as part of a botnet.
Wow, that's some scary stuff. It really puts things into perspective. But I have to ask, if this vulnerability was so dangerous, how come it went unnoticed for so long?
That's a great question, and it speaks to the complexity of modern software.
Yeah.
CLFS is just one small part of a vast and interconnected system. And it's not always easy to foresee every possible way that code might be misused.
So you're saying that there could be other vulnerabilities like this lurking in other parts of the operating system just waiting to be discovered?
It's certainly possible. The truth is, with millions of lines of code in a modern operating system, there are bound to be vulnerabilities that haven't been found yet. It's a constant game of cat and mouse between security researchers trying to find and fix vulnerabilities and attackers looking for ways to exploit them.
That's a little unsettling, to be honest.
Yeah.
But what can we as everyday users do to protect ourselves from these kinds of threats?
Well, the first step is awareness. Understanding that these vulnerabilities exist and being cautious about what you download and the websites you visit is crucial. Keeping your system and software up to date is also vital, as those updates often include security patches that address known vulnerabilities.
So it's kind of like practicing good digital hygiene. Wash your hands, don't click on suspicious links, and keep your software clean.
Exactly. Those simple steps can go a long way in reducing your risk. And if you're really concerned about security, you can always use additional security software like antivirus programs and firewalls to add another layer of protection.
Good advice. But thinking back to this specific CLFS vulnerability, it seems like it relied on a pretty unique set of circumstances and a lot of technical skill. Isn't that a high bar for most attackers to clear?
While this particular exploit is quite sophisticated, it's important to remember that attackers are constantly developing new techniques, and as new vulnerabilities are discovered, exploits become more accessible.
So it's like an arms race.
Yeah, in a sense, security researchers are constantly working to identify and fix vulnerabilities, while attackers are always looking for new ways to bypass those security measures.
Well, that's a bit daunting, but it sounds like we're not completely helpless. There are people working hard to protect us, and as long as we stay informed and take precautions, we can minimize our risk.
Exactly. Security is a shared responsibility. It's up to developers to write secure code, security researchers to find and report vulnerabilities, and users to be aware of the risks and take steps to protect themselves.
Well said. So to wrap things up, we've taken a deep dive into the fascinating and somewhat scary world of CLFS vulnerabilities. We've explored a complex exploit that highlights the potential consequences of even minor coding oversights and gained some valuable insights into the ever-evolving landscape of cybersecurity.
Remember, everyone, security is a journey, not a destination. Stay curious out there and stay safe.